I hope all of you are doing good. I am Mr. Ish. Thank you for joining me. In this video, I want to share a very interesting infinite geometric pattern with all of you, having a good mathematical basis and foundation to it. A mathematically derived infinite geometric series pattern. You're starting here with an x and y axis, and that's your origin. We will develop a square first. The square has a side dimension of 1. I have a table over here of values which will demonstrate an infinite geometric sequence. The sides of the square, the radius of sectors, and the arc lengths of those sectors. I'm starting here with the side of a square to be 1. Where is the sector coming from? Well, this here represents a center of a potential and many potential circles and the vertex of many potential sectors that I will draw. From this point to that point, I'm demonstrating an arc. This arc is part of a sector. You see, theta in all instances is always equal to pi over 2. And in all instances, these are the circle centers because these sectors could have been continued all around to complete circle. The dimension here is 1 on all sides because it's a square. Therefore, the radius must also be 1 because the radius in every instance will always share the same dimension as the side of its corresponding square. How is my pattern going to develop? Well, I have an imaginary y equals x line, and this is it. At the intersection point of any of my arcs and the y equals x line, I'll demonstrate a new square. And then from that square, I'll create yet another arc. Because that arc will create a sector, but it will also be part of an imaginary circle. So this origin always serves as a vertex or a center. When I'm looking here at 1 and 1, you know, theta is equal to pi over 2. My arc length is pi over 2. These values will always be the same and the arc length will always be different, but each of those corresponding columns will have an infinite geometric pattern develop. My first row is complete. Now let's do the next one. For the next one, I have to get the dimensions of this square, but you can easily get the dimensions of the square by always figuring out the intersection point. Y equals x and this arc. This arc is coming from a radius of 1. And a unit circle, x squared plus y squared is equal to 1. You solve for y, it's equal to 1 minus x squared. If you determine the intersection point of these two, you'll get the dimensions of the next square. And that's always the cycle over there. You'll always cycle through an intersection point for the imaginary line y equals x and the intersection of the corresponding arc. And that will give you the dimensions of that square and the radius. Anyhow, you're seeing x is equal to root 1 minus x squared. 2x squared is equal to 1, x squared is equal to 1 over 2, and x is equal to 1 over root 2. I did some mental math and I skipped steps. Anyhow, this is the dimension over here, 1 over root 2, and it will also be the dimension of the radius, and then you know this will be pi over 2 root 2 based on r theta. Again, remember the intersection point of any of these arcs with the imaginary line will always give you the dimension of the next square you draw. Now I'm going to draw yet another square and then I'll create another arc length. If I get this intersection point, it'll give me the dimensions of this square and the radius sector. What's the equation of that arc? Well, it's coming from a square with the side 1 over root 2 or a sector with the radius 1 over root 2. X squared plus y squared is equal to 1 over root 2 squared, which is 1 over 2. Y is equal to 1 over 2 minus x squared root, and then always y equals x. You're doing the intersection point of these. You'll have x squared is equal to 1 over 2 minus x squared. I took the root on the other side. 2x squared is equal to 1 over 2. X squared is equal to 1 over 4. And then x is equal to 1 over 2. My next set of figures is 1 over 2, 1 over 2, and then this will be pi over 4. I have 3 squares drawn, therefore I have 3 rows of dimensions. And now you're getting the idea. Always at the intersection point, we're creating a new square and then a new arc. And then at the next intersection point, we're creating a new square and a new arc. And then at the next intersection point, a new square and a new arc. And here's my infinite geometric pattern, which is developing and having a mathematical basis to it. I don't need to start doing any more intersection points and calculations because everything can be extrapolated. We have a common ratio over here developing, always a given term and the term before. Look at this column right over here. Any of these two columns, you'll see 1 over 2 divided by 1 over root 2. This divided by that. We'll have 1 over 2 times root 2 over 1, which is root 2 over 2, and that's equal to 1 over root 2. I'm seeing a common ratio over here of 1 over root 2 with regards to the dimensions of the square side and the radius of the sector. It's the same common ratio also developing with regards to the arc lengths. Pick pi over 4 and divide it by the value before. Pi over 2 root 2. and then I'll have pi over 4 times 2 root 2 over pi. And what do I have? I have a root 2 over 2, which is 1 over root 2. So this common ratio is applying to this side of the square, the radius of the sectors, and the arc length. So now we indeed have proven we have an infinite geometric pattern at play. You can easily develop more rows based on the extrapolation. This next one will be 1 over 2 root 2. This will be 1 over 2 root 2. This will be pi over 4 root 2. The next row will be 1 over 4. This will be 1 over 4. This will be pi over 8. You're seeing a clear infinite pattern develop, a geometric pattern. We can establish everything in terms of a rule. With regards to the sides of the square and the radius of the sectors, I have a rule which is looking like this. It'll be from n is equal to 0 up to infinity, 1 over root 2 to the power of n. That's my rule. You can easily do a sum calculation because you have a common ratio here which is less than 1. Therefore, you'll have a finite sum of series, and you can do that by a1 divided by 1 minus r. That's your formula. Here's my a1 term, a1 term, and a1 term. This is the rule for the sides of the squares and the radius of the sectors. And with regards to the arc lengths, you're seeing another interesting rule develop based on those values. It's n is equal to 0 and infinity. Your first value is a pi over 2. I can do pi over 2 times 1 over root 2 to the power of n. But if you want, you can push the pi over 2 outside, and your rule can be pi over 2 from 0 up to infinity, 1 over root 2 exponent n. And you run through this rule, you'll easily see those values. You have a finite sum of series with regards to the sides of the squares and the radius of the sectors. You have a finite sum of series with regards to the arc lengths. All of these three specific items here have a clear infinite geometric series pattern developing. Thank you. Have a good day. Bye.